Let's begin. 27 seconds earlier. Slides for the regression have been posted. Okay, so I don't get in trouble with everyone. The lectures from Tuesday have been processed. I will post them, put them on YouTube immediately after class, and I will process this lecture today and post it by tomorrow on YouTube, so you have everything you need to study for the exam. Some of the material I covered on regression, a couple of points are not in your textbook, so make sure you watch the lecture or pay attention here definitely and rewatch the lecture. The data analysis Google Sheet thingy from last week for regression, I added some more data to it. Now, because you made a copy last week, you're not going to see those data, so I will ask you to go back to that link and just copy whatever new sheets there are or I added, or just re-download it, because we really didn't do much work on it last week. If you remember, all we did was compute the correlation coefficient for these things, and those were already included in the Google Sheet. So I will ask you to just go back and download a fresh copy of that Google Sheet so we can work with the new data we need to work with today. Last week we left off talking about linearity, looking for linear relations between dependent and independent variables in just one independent variable and one dependent variable. And we focus on linearity because that's a simple, these are the simplest types of data, the simplest types of analysis we want to do. Almost all statistical analyses start by being based on linear analysis. So it's important to identify linear relations, linear trends in data. And we computed this correlation, the Pearson correlation coefficient, which we called R, and R was between -1 and 1. And if it's closer to -1 or 1, it indicated there's a strong linear relation between the X and Y data. If it was closer to 0, it indicated either nonlinear or no linear relation between the two data, okay? The two variables. And in Google Sheets or Excel, you can do Correl or Pearson and make sure you give it the Y data first and then give it the X data after so that you can compute that correlation coefficient. Now we're going to take this one step, take it up a notch, and actually do a hypothesis test to see if to check if the data is actually linear or not, rather than just going by the value of R. Because what if R is 0.5? It's like, you know, it's like in linear purgatory, right? Is it really linear or nonlinear? So how do you determine that? You have to set a standard, and that standard we're going to set with a hypothesis test, okay? I like that linear purgatory. Like, are you linear or nonlinear? Or okay. So, and the only test we're going to do is not whether the slope of the data is positive or negative. I don't care about that. What I care about is whether it's linear or not. I'm not worried about the slope because I get that from the value of R, if R, or just looking at the data. If R is positive, the data has a, is positive slope. If R is negative, it's got a negative slope. So our hypothesis test is going to be with the null hypothesis that there is no linear relation between the data, and that implies in a hypothesis test, remember, we're making a statement about the population, okay? So in other words, I have a sample, I calculate R. What can I say from R? What can I say about rho, which is the correlation coefficient for the true population? Okay, what can I say about the linearity of the X and Y data in the population itself? And our null hypothesis is that there is no linear relationship between the data, between the X and Y, between the dependent and independent variable. Rho is equal to 0. Okay? Our alternative hypothesis is that rho is not equal to 0, which means there is a relation between the data. It will be linear. Now, how linear do we want it to be? That is going to depend on our significance level, on our alpha. Now, when we see a not equal to in a hypothesis test, this immediately implies a two-tailed test where alpha over 2 is in the left tail and alpha over 2 is in the right tail. And you can do a p-value analysis, or you can do a rejection region. I like the rejection region myself, and that's done essentially by computing your sample statistic based for R and then comparing it with the critical value. Remember, the critical value is based on the significance level, has nothing to do with the data, it's just a significance level. However, our sample statistic for the correlation coefficient is actually based on a student t distribution, and is given by this statistic, t equal r over square root minus 1 minus r squared over n minus 2. R, so you know the data, n is the number of points in your data, and n minus 2 is going to be your degrees of freedom. R is your Pearson correlation coefficient for the sample, so you can totally compute this t statistic. Okay? Now, if t, for a two-tailed test, if t less than t minus alpha over 2, that's the negative critical value, or greater than t alpha over 2, then you are in the rejection region. Okay? Mathematically, all you have to test for is whether the absolute value of t is greater than the positive critical value, greater than t alpha over 2. So that's the simplest way of presenting this. Or you can still do a p-value like we did before for a two-tailed test. I'm going to just follow the rejection region approach. Okay, so one more definition before we get into some examples. The square of the correlation coefficient is called the coefficient of determination. Now, in numerical methods, we deduced that after we did the regression analysis and deduced that from the formulas, etc. This is here given to us before we even do regression. And it comes from a statistical analysis, a little more advanced. And the coefficient of determination is a measure. So this is a different definition than we saw in numerical methods. And this is actually a really cool definition. It's a measure of the proportion of the variation in the response variable, in the y values, that can be associated with variation in the explanatory value. So I'll give you an example. If the correlation coefficient, between the number of cups of hot cocoa sold at an outdoor skating rink and the average temperature outside is R equal minus 0.65, how much of the variation in the number of cups of hot chocolate sold can be associated with the variation of temperatures? You might imagine that as the temperature drops, people are going to have more affinity to buying hot cocoa, right? Because it kind of keeps them warm, makes them feel fuzzy, etc. Right? So in analysis on that, the number of hot chocolate cups sold as the temperature decreases is R equal 0.65. Okay? And so that's going to look like as the temperature decreases, there should be more hot cocoa sold. And then, okay, so then in that case, how do you, just from R, you can answer that question. If you take R squared, it gives you 42.25% as an answer. Then you could say approximately 42.3% of the variation in the number of cups sold can be associated in the variation of average temperature that evening. So almost 50% of your sales are affected by changes in the temperature. That's a big deal. So make sure you plan when you put your hot cocoa stand out. Okay? All right, like cold water and temperature, or ice cream and temperature outside, right? There's going to be a strong relation there. Like as it gets hotter, or you're on the beach, right, and it gets hotter, you want ice cream, or the number of children you have and how many ice creams you buy. So, all right. So we start with some examples, some lightweight examples, and then we're going to ramp it up real quickly. We'll do one example on just this significance for R, and then immediately we're going to jump to regression and do like a full-blown regression analysis. Okay? Here's a question. Here's a problem from your textbook. Use a hypothesis test to determine if the linear relation between the number of, I think people make a mistake when they use the word relationship when they're describing data. I actually made a comment about that a few years ago in one of my lectures that, there's no relationship between X and Y. They're not like dating or anything. It's a relation between X and Y. Y has a relation with X. So, and I don't know, many textbooks still use the word relationship. X and Y are not persons. So anyway, so the linear relation between the number of parking tickets a student receives during a semester and then the student's GPA. This is a funny one. So is there a relation between how many parking tickets you get and your GPA? It's not causation, it's just a correlation. There's a relation between the two. So there's no causative effect here, okay? So so no causative effect, but maybe. During this, like you're rushing to get to the exam and you get a ticket just because you want to make it to the exam, but then, you do well, you don't do well, or maybe you should plan a little ahead, I don't know. So during the same semester, statistically significant at the 5% level of significance. Okay, so I have the data for you already in your Google Sheet, and this is a plot of it. So let's go on Google Sheets, plot it, and do a significance test together. And I think I already have the answer in there already for you. So let me see, regression analysis, data. I think I already have the data, the answer in there. So I'm going to actually make a copy. And I'll work on the copy with you so you can see what I'm doing. So we'll program this one and then just copy and paste it for all the other cases. It's just going to be plug and play, okay? Now, this is the spreadsheet. Let's expand it a little bit here. And maybe zoom in 125%. So if you look down, we have a bunch of data. This one, tickets and GPA data. Okay? So if you want, you can leave these as is or just go ahead and delete them so that you understand how we're going to build this together. First thing I like to do is just go ahead and plot the data, because when data is spotted, it better be plotted. Okay? Okay, let's see. Okay, so now Google Sheets remembered that I like scatter plots. Okay, so yeah, there is some linear relation. There's a trend, right? And I think there's a relation. It's not very strongly linear, but the trend is linear. As this increases, this is decreasing almost at the same rate. So we'll see how what the hypothesis test tells us. Okay. So let's go ahead and start with that. So the first thing is to compute my correlation coefficient. I'm going to do equal correlation. And my data Y, I'm just going to pick B and pick the entire column, because what you can do now, you can use this sheet as a calculator. You copy paste new data, it will automatically do the calculation for you. Okay, so you just select the entire column, and then it will automatically get rid of the zeros. Essentially, they're not going to affect the calculation. Okay, and same thing for the X data, which is in the column A, and you type enter, and you get minus 0.58 or minus 0.6. Indeed, there's a negative slope. So yes, I agree with that answer. And it's like in that purgatory territory, right? Is this linear, significantly linear or not? I don't know. So next, I need to calculate the R squared value, and that's simply this guy squared, okay? Oops, nope, not star. I'm using Python, never mind. To the power 2. That's R to the power 2, so that's D2 to the power 2. Or you can also do equal to coef, or never mind. I forgot what they call it in Google Sheets. Okay, never mind. Now n is my number of points. Okay, so how do you do number of points variably? What if I have 50 data points or 1,000? Right, I don't have to worry about that. So, count. Yes, thank you so much. Yep. So we're going to do count equal count, or like 1, 1, 2. I can't believe this is still a thing. Like 30 years ago, you should look up the lemon version of it. I don't know if you're familiar with that. Anyway, it's a funny one. Okay. All right. So we'll do count, but on the entire column. Okay. Whether you do it on A or B, it doesn't matter. It will only count numerical values, so it's not going to capture the label at the top. Okay, it will only count the numerical values. And this one is going to give me 15. Indeed, I have 1 through 15 data points. Okay. Now, degrees of freedom is n minus 2, so it's that guy minus 2. My t-statistic is whatever I had in the formula. So let's bring up the formula. It's r over square root of 1 minus r squared over n minus 2. OK, good. So this is equal to r over square root, open parentheses, oops, open parentheses, space, 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 square root of 1 minus r squared, 1 minus, let me put another parentheses here, 1 minus r squared, which I already calculated here. Oops, I already calculated here, over degrees of freedom, n minus 2, which I already calculated there. Okay, right? So it's r over square root of 1 minus r squared over n minus 2. Right? So it should be minus 2.61. So that gives me my t-statistic. It's on the left. Now, I need to do a two-tailed test in this case. All right? So I need to do a two-tailed test. So you can either check if this is only on the left side of your critical t-value, etc., or you can just do the absolute value, one that I describe here. If the absolute value of your t-statistic is greater than your positive critical value, then you are in the rejection region. Otherwise, you're not. So my alpha is 0.05. My critical t, remember, this is based on the alpha on the significance level. Because this is a two-tailed test, I'm going to do t dot inverse, and I'm going to do a two-tailed test, t dot inverse dot 2t, and all I have to do is give it alpha, so it's going to split it in half. It's going to do alpha over 2 on the right, alpha over 2 on the left. Be careful, don't give it alpha over 2. Don't give this one alpha over 2. Okay? And degrees of freedom, it's right here. Now this gives me the positive value. It's going to give me the positive value for the critical t. Okay? And then finally, my decision is going to be if the absolute value of my t-stat, if that's greater than my positive critical value, then I reject the null. What this means, I have a significantly linear relation. Okay? I'm going to call this significantly linear. Otherwise, not significantly linear. And this one says, indeed, we are significantly linear. So from here onwards, we are not going to proceed with any regression analysis unless we are significantly linear. Unless r, regardless of it might be 0.3, but based on your significance level, it might tell you it's significantly linear. So you're going to take that and move on and then do the regression analysis. You might have more tolerance for certain types of data and allows you to take larger significance levels, right? Could be 10% maybe, okay? So this is significantly linear. It's a good thing, all right? And yep, that does it for this exercise, for this example. Okay. Next, we move on to actually doing regression. So far, we're just still flirting with the data, asking whether it is linear or not, and to what significance level. Okay? Now, remember the hypothesis, the test that we just did, is not that the sample data is linear. It's actually that the population of students the entire population of students have a significantly linear relation between number of parking tickets and their GPA. It's not causation. The high GPA doesn't cause less parking tickets. Correlation is important in that sense. It's just they're just correlated. Okay, but we're not saying anything about causation, if one causes the other or not. Okay, that's a little harder question to answer. All right. Now we're on to actually develop. Now I want to develop a model. So for example, what I want to ask next is, if you pick a random student from the U, and you ask how many tickets did you have, young student, and they say like I have 3.5 tickets, or like what's half a ticket, like ticket that was torn apart, maybe I don't know. So let's say they have 4 tickets, right? Can you tell me their GPA? Okay, so that's the next question we want to ask. You can't do interpolation because the data is all over the place. You cannot just pick 2 points. What do you interpolate between these 2 points or those 2 points or those 2, right? You can't. We need to build a model. We need to build a formula to say, oh yeah, the behavior looks like this, and then we can make a prediction. Okay, so that's what we're after next. It's called the least squares regression line. Okay, for those of you who haven't seen it, for those of you who have seen it, okay, this is another way of looking at it. If you've done Excel, you might have seen trend line. Okay, so that's the trend line. This is where it comes from. All right, so we can develop a model curve. In this case, it's going to be a straight line. In numerical methods, we took this to the stars. We built sines and cosines and arbitrary basis functions. So you know all the math for that. You can apply the same statistics to those, but they get incredibly harder. But for basic statistics, even advanced statistics, a straight line is a great statistical tool. So what we want to do, if the data is significantly linear, then that's great. Next, we're going to model it with a straight line because it's linear, right? So we're going to model it with a straight line. The power of that straight line is a simple formula. It allows us to make predictions at intermediate data points, etc. Okay, so the method that we will use to develop that straight line is called least squares regression, and I'll try to explain that really quickly of why we call it that. Some of you already know that because we did this derivation in numerical methods, but we're going to look at it differently right now. So suppose you have these data from your sample, y as your dependent variable on the y-axis and your independent variable on the x-axis, and these data are given to you in pairs, x1, y1, x2, y2, x3, y3, and so on and so forth, and data points. Okay, that's your total number of points. What we want is we want to put a model curve in between those data somewhere. I don't know the slope. I don't know the intercept. It could be going up like this. It could be like this. It could hit 0. I don't know where it's going to hit. All I know is I want to put a line to capture the trend of those data. Is it going to hit each and every point? No, absolutely not, because we're capturing the trend. It cannot hit each and every point. Look at those points. They're all over the place. Could it hit 1 or more points? Absolutely. It can hit 1 or more points, but that's just pure chance. Okay? So I want to put this model curve. Typically, we write it as b0 plus b1x. You might find it as mx plus b or a0 plus a1x. Don't freak out when there's a change in nomenclature, or alpha x plus beta. Okay, so don't freak out when you see a change in nomenclature. It's just simply slope and intercept. The slope is b1 and the intercept is b0. Okay, so how do we capture this model curve? What we do, we say, okay, this model curve is obviously off from the true data that we sampled. Okay, so this line, so the value at x1, what we measured was y1, but what this line is giving us a different value, correct? So let's call that y hat 1. And then for this guy, it's going to give us y hat 2. And for that guy, y hat 3, and so on, all the way to y hat n. Those are the model predictions at the input data points. For x1, my input data was y1, but my model was y hat 1. For x2, my input was y2, but my model gave me y hat 2, and so on. Now together, these y1, y hat 1, y hat 2, and y2, etc., they define what we call a residual error. This is the error committed by using our model to represent the input data as the difference between the model prediction and the input data. Right? The input data is treated as the truth, although there's variability in it, but forget about that for a minute. My model is not returning my input data, it's committing an error. okay? And it's committing an error at each and every point. So a residual error. So we call the first error R1, R2, R3, all the way Rn. So we call it Ri. This is the residual at the ith data point. Okay? Now the idea of the idea is that together, all of these errors, if we compute a sum of their squares and minimize that total error together, we get what's called least squares regression. That's why it's called least squares regression, because it's minimizing, it's finding the least value of the sum of the squares of the errors. These are the errors, yi minus y hat I at each point. Sum them up, sum their squares. That gives you a total error. Minimize that. So find, in other words, find B0 and B1. Find that line that minimizes this error. Okay? If you're taking numerical methods in the fall, you're going to learn how this is done with linear systems of equations, etc. But I'm going to give you the answer over here, is that these are the formulas for a straight line. You're given x and y data. You can analytically, this is one of the few cases where you can analytically find an answer for the intercept and the slope. So the slope is given by this guy, and the intercept is given by this formula. Okay? You know all of these values because you know the x and y data that's given to you in the sample, n is your sample size, and so on. Okay? Now, luckily, we don't have to compute those, we don't have to program those in Excel or Google Sheets or Python. Python, we might have to, but in Google Sheets, we have all of that already pre-programmed for us for any given data, so we can immediately get those values. Okay. Now there are 3 examples in the slides that you can work through. There's 1, 2, 3, but the example I want to get to is this guy because it covers all of the other examples and a little more. All right. So the following table gives the average monthly temperature and the corresponding monthly precipitation totals for 1 year in Key West, Florida. Okay, so you have average temperature and precipitation. Now, why I picked this example? Because it has all the questions that are covered incrementally in the other examples. So now you can go back and work through the other examples, which are in your textbook as well, and compare notes and try to work yourself with the Google Sheets that we're going to develop together. So first they ask, create a scatter plot of the data. Does it appear to be linear? Calculate the correlation coefficient. Verify that the correlation coefficient is statistically significant at the 0.05 significance level. Determine the equation for the line of best fit. Calculate and interpret the coefficient of determination, R squared. If appropriate, predict the monthly precipitation in Key West, etc. If appropriate, for each additional degree that the temperature rises, what is the increase? Okay, so we're going to answer all of those questions in Google Sheets. All right? So we're going to go in Google Sheets. You already have some of the answers over here. Some of the you already have the data for the other examples. Well, hold on. Number. Uh-oh. Did I not put the data for the precipitation and temperature? No way. Oh my gosh. What? Okay, give me a second. What? All right, so I don't know what happened. I probably deleted that sheet. My apologies. So let me actually get you the data. Give me a second. So I'm actually going to copy the data from here, and I'll give it to you in a format. All you have to do is go back to refresh the sheet and just copy and paste the data, okay? All right, so where is it? So now what I need to do, I need to transpose this table in Google Sheets, and then I'll give you the data. Okay, give me a second. Okay. delete. Create another sheet. Oops. All right, so this should be problem example 12.2.5. Okay, so now go back to the Google Sheet that I shared with you and just copy the data. Okay, just copy the data from that sheet. So if you're already in there, on there, so you should see this at the bottom, 12.2.5. This is the data, okay? Can you see it? You refresh, you might need to refresh. Okay, great. Copy it to the sheet you're working on, okay? My apologies. We lost like 2 minutes. Stupid. Okay. All right, so I'm going to call this in my worksheet 12.3.5 or whatever that number was. Okay, whoops. I'm going to copy this data and paste it over here. Okay, so the first thing that I want us to do is plot the data, and we're going to do insert chart, and we're looking at precipitation, right? So we're looking at precipitation versus average temperature. Okay, precipitation total versus average temperature. All right. Well, it kind of starts flat and goes up. So there's a slight parabolic trend early on here. But then as the temperature increases, it becomes strongly linear. So I think there's possibly a linear trend. We can do a hypothesis test to see if that's satisfactory. Okay. What we already did the work for this, so we're going to go back to the tickets and GPA, and notice here at the C column, just copy these guys, Command C or Control C, and then go back to that precipitation problem. All right, and then put it right here. I'm going to move this guy down. Just put it right here, paste, and it does the work for you. Okay, it just did it for you. And it's telling me it is significantly linear. The correlation coefficient is 0.86. The R-squared value is 74%. So in other words, 74% of the variation in the precipitation can be explained through variation in the average temperature. Okay, that's a lot. So there's this very strong connection between the precipitation and the temperature, which could indicate some causality, okay? Everything else is automatically calculated, all right? So everything else is already done for us, so we don't need to dwell on that. Okay, so next step is we're actually going to do regression analysis. So I'm going to add this here and say regression analysis. Okay. Or actually, hold on. Let's call this regression, okay? Let's call this regression, because next I want to find that straight line. We're going to do it in 2 ways, and those 2 ways are going to hopefully confirm that we're using things correctly, we're doing things correctly. So we're going to go to the data, to the chart itself. In Excel or Google Sheets, you can build a trend line on any chart. Okay, if you go on Edit Chart, and you go to Customize, and then you go to Series, and then you scroll down, and there's this thing at the bottom called Trend Line. Click it. Okay, click it. If you click Trend Line, bam, it's going to plot a trend line for you. You can change its color. That's about it. Make it red. And you can choose whether linear, exponential, polynomial, etc. We're just going to stick with linear, okay? Because that's what we're doing. Regression to straight line, which statisticians call linear regression, but we know, other types of regression can also be of the linear type. Anyway, don't worry about that. But just choose linear regression, okay? And it plots the line for you. But I'm interested in the equation because this is useless to me. Okay, it's a straight line, but then what is my precipitation at 84 degrees. I don't know. I need the formula for that straight line. So you can get that formula. Just scroll down a little bit. And you could say label, use equation. So this is telling you what do you want to label the straight line as. Use the equation to label it. So that's telling me that my line has the following formula. 0.225x minus 15.4. So the slope is 0.225 and the intercept is minus 15.4. Okay, that red line. And it can actually show me my r squared value. You show r squared, it's telling me r squared is 0.738. Now look at the r squared that I computed here, 0.738. Good, good. Okay. But still, now I know the equation. I need to program it in Excel or Google Sheets to be able to make a prediction. Because I still want the temperature at 84, the precipitation at 84 degrees. Okay? So there's two ways to do this. Either you go and do it the silly way where you first do the trend line, read the equation, and type it manually. Or do it the smart way and let Excel do it for you automatically. So what we're going to do, we're going to use built-in functions in Google Sheets or Excel, they're the same, to capture the slope and the intercept automatically without having to actually do this and go and hard code it. Hard coding things, you're going to get in trouble. Okay? So we're going to add two more variables here, slope and intercept. Intercept. Okay, I'm going to move them to the right. All right. And then all you have to do here is say equals slope, right? And then data y, and then data x. Now select the entire column so that if you copy paste other data here, it will automatically do the calculation for you. Indeed, my slope is 0.225 as expected from the trend line. Consistent, good, things make sense. Same thing for intercept. It's called, guess what? Intercept. Again, data y, and then data x. Okay. And it's minus 15.4. Same thing as in the equation that I saw. Now I can use slope and intercept to make a prediction. Okay? To make predictions, I'm going to need to create a new column here because we're going to build also intervals on the predictions in a minute. Predictions. Now, I want to predict at a given x value. So let's say I want to predict at 84 degrees or 83 degrees, 84 degrees, okay? And my model needs to give me a value. So model prediction. So that's my linear regression model prediction. Let's put these, make all of these go to the right. And make all of these go to the left. A model prediction that's equal to slope times my x value plus intercept. And then my model prediction tells me that at 84 degrees, I expect the model is predicting 3.4 inches in precipitation. So at this, that's going to be this point at 84. This is going to be at 3.5, about 3.5, okay? Now, if I go to 85, it's not going to give me the blue points. It's just going to give me the red point, okay? It's not going to return the value. This is a model, okay? There's an error in it. That's it about doing a regression line, okay? Now, because we're doing statistics, so first I make sure, are we all synchronized? Okay, great. Now, because we're doing statistics, that's not satisfactory. We need to assign a margin of error for all of these values. And from a statistician's perspective, everything is random. You know, even the confidence intervals, you can build confidence intervals on top of confidence intervals. So you imagine. So everything is a random variable, has a confidence level. So now the idea is, could we build a confidence interval around the values that we are predicting, okay? And more specifically, this value that I predicted at 84, okay, is it a single value at at temperature 84, or is it an average? Right? It can be interpreted in both ways. So one interpretation is to say, from my regression, I want to interpret the precipitation at 84 as the average value of precipitation across all years or all times when the temperature was 84 degrees. That will automatically lead to interval estimation. Then you build confidence and say, on average, for all years or times when temperature was 84, this is what I expect to see for the average value of precipitation. Or you can say, if I pick any one year or any one period where I have 84 degrees for temperature, what is my precipitation? Well, the model is going to give you a value, but there's also a margin around it. And that's not going to be a confidence interval. In statistics, we call it a prediction interval. Okay, so that's the only little thing that we're going to add. So the textbook only talks about prediction intervals, and it kind of conflates them with confidence intervals. But there's two things going on here. When you predict a value from your regression line, you either interpret it as a representation of the mean value of the population, like what is the mean precipitation for all times when the temperature was 84. Then you have a confidence interval there, because the confidence interval tells us with 95% confidence, the mean value of the population is going to be there. Okay? Or you can ask the question, for one given point, one given year, one given time, what should I expect the precipitation to be at 84? Then that changes the range significantly. It's going to be called a prediction interval. Okay, so we're going to do those two things next. They're not very, very hard, just a couple of nasty formulas. And once we're done, that'll be mostly it. Okay, confidence and prediction intervals. Okay, so first the residual is y minus y bar, which we already defined. And then the error was yi minus y bar I, y hat I squared, which we also defined already when we built the regression. Okay, now the margin of error, or the standard error of the estimate, is essentially the standard deviation in the errors. So when you take all the errors together, all the residuals, what is their standard deviation? This is their standard deviation. It's the square root of the sum of the error squared over n minus 2. And again, my degrees of freedom all the time over here is n minus 2. Okay, and this tells you yi. We know yi as the input data that was given to us. Y hat is the prediction data that we were predicting. Okay, and then n is the sample size. A prediction interval, now we define a prediction interval, is a confidence interval for a single value of the response variable at a given fixed value of the explanatory variable. So I define these two here, try to make the distinction. A confidence interval tells you something about the mean of the population, and a prediction interval tells you something about an individual in the population. So what I'm going to do next, I'm going to imagine every point on the regression line as if it belongs to a different distribution. Can you imagine the dimensionality of that? Imagine every point at the regression line belonging to a different population, different than any other on the regression line. And you can then build a confidence interval and a prediction interval at each one of those points. Okay, at each one of those points. Now, the margin of error is for a confidence interval is given by this formula. So it's similar to the margins of errors that we did before when we did confidence intervals. There's a t value, and then there's a standard error, but then there's a square root of something. Just use it as it is here, because this is going to be, it's based on the standard deviation of the residuals, etc. So for a confidence interval, this is your margin of error. And we're going to use that plus or minus the value predicted in the model. So we're going to predict a value in the model. If you add and subtract this value, it gives you a confidence interval. That's it. That's what I'm saying here. And then the meaning is, when you're working with a confidence interval, what we mean is that for all years when the temperature was 84, all times, the average precipitation has this confidence interval. Okay? If you want to do a prediction interval, You just simply add 1. Look at how the formula changes over here under the square root. It increases it significantly because you're asking a question about a single instance in the population. So you have a lot more uncertainty than the average across all years. Looking for prediction, you compute this error and add it and subtract it to the predicted value from your regression line. That's it. So if you're doing a confidence interval plus or minus E based on the confidence interval error, prediction interval plus or minus E based on this formula. Okay? So in summary, confidence interval, you use this margin of error. Prediction interval, you use that margin of error. And then simply subtract it and add it from your y hat value. Remember, y hat was the value predicted by your regression model. Okay, now we're going to go back to the problem of height versus femur. Who remembers that problem from numerical methods? Yes. So in numerical methods, for those who were not in numerical methods, when we studied regression, we looked at data relating a person's height, predicting a person's height simply from their femur length. So there's a strong correlation between the two. So if you're extracting, cadavers, etc., you can make a prediction about a person's height just simply from their femur length. Okay, and we actually did run an experiment in class. We measured femur lengths and looked at the prediction, etc. I have a lot more data over here. Forget about the yellow and the blue bands for a second. If you look at the cluster of data, looking on the y-axis, a person's height in centimeter and femur length also in centimeter, there's a strong relation between, as the longer your femur length, the longer you are in general. There are exceptions because there's a lot of, for femur length of 45, you had like 7 different heights, right? But there's a trend in general. The data is increasing as femur length increases. Now, the regression line, the least squares regression line, is the one in blue. Okay, is that straight line in blue. Okay. Next, what I did for each value, so I have when I plotted this line, I put in 100, 200, 300 values here. Okay, I put in 300 values, make it pretty, so you can plot the line nicely. For each value, I went and computed a confidence interval and a prediction interval. The confidence interval is shown in blue, in this blue band, and notice how it shrinks and kind of expands as we go away from the center of the data because we have a lot more uncertainty away from the data. But as you get closer and closer to the center of the data, you have more certainty, so your confidence interval starts shrinking. But your prediction interval is in this yellow band, and it's much wider, and it hardly changes. So again, it depends on the question you're asking. If you say that my person's height at a femur length of 45, person's height is 162, let's say, with a confidence interval of 160 to 164, let's say, then the word confidence interval says that on average, the population of people with a femur length of 45, they have a mean height that's going to be in there with 95% confidence. But if you just randomly pick a person and whose femur length is 45 centimeters, then you're going to be working with the yellow band. If you ask the question, if I pick a random person from the population whose femur length is 45, what is going to be their height? It's going to be anywhere in between the yellow band. Okay? So that's the distinction that you have to distinguish. It gives you a level of uncertainty. I know that their height is going to be 162 plus or minus 10 centimeters maybe, because you're doing a prediction for a person, not a population. Okay? Confidence interval, population. Prediction interval, just a single individual. It's very important. There's more variability in a single person. It's just one person. Yes? Not all the data. See, these data are outside. They're not outliers. These data are just going to be outside that, because based on your confidence level. This is 95%. If I expanded it, it's going to be wider and wider until it reaches infinity, right? So as your confidence level goes to 1, your confidence, your interval becomes infinite, right? Yeah. But at 95%, it didn't capture those points. If I tighten it more, if I make it 99%, it's going to become wider and wider. Okay? Just distinguish between the two. Okay? Distinguish between the two. All right? So let's do this together in Google Sheets. Okay? So we're going to go to this height versus femur data. And I already copied this thing over here, so we're good over there. But let's plot the data. So insert chart, and it's going to do it for me. You can adjust the y-axis and whatnot. I'm not going to worry about that right now. But if I go to trend line, series, and add a trend line over here, I'm going to make it in red. And make line opacity 100. Make it like 4 pixels wide. OK, so that's my trend line or my regression line. And I'm going to show the r-squared value and the equation. The equation says that a person's height is, based on this model, is 2.83 times the femur length plus 40 in centimeters. OK, and my r-squared value is 0.72. What's going on here? Okay. What's going on here? Yeah, this is not a copy and paste. Sorry about that. This is bad. Actually, I'm going to copy. What did we just do here? Yep, I'm going to copy these guys here. I'm going to copy these and just put them on the height femur. Uh-oh. Okay. Why are you doing this to me? Ah, this one, sorry. I make these mistakes on purpose to teach you a lesson. OK, now it's all well with the world. OK, right? So I knew that I had a mistake because my r-squared didn't match this r-squared, and now all is well. And indeed, my slope is 2.827, which is 2.83 rounded over here. My intercept is about 40, which is what the equation is giving me. My r-squared is 72. So what this means is 72% of the variability in the data of people's heights is explained by the variability in the femur. Okay? A prediction, then, OK, we can make predictions. But now I'm interested actually in the errors. All right? In the errors. Now, to do this correctly, I actually need to compute a few things. And if I go back to my formulas, because we have to do this by hand, OK? So if I go back to my formulas, I need a lot of things here. First, I need, OK, so for this, I need, so T alpha over 2, I already have that calculated. I need SE, which is the standard error of the estimate. And that's this guy. It's square root of this difference squared over n minus 2. OK, so I'm going to need a couple more columns here. So what I need to do is actually move this. I'm going to cut it and put it over here. Because I need 2 more columns here to compute y hat. OK, to compute y hat. I'm going to do y hat. So this is really your final, this sheet is your final regression sheet that will work for all XY data. Okay? You can ditch all of the other ones. This is your final sheet. So this is y hat. What is y hat? Is my model prediction at the input X data. Y hat is applying the regression line on the X data. OK? OK, you do it. All right, so we're going to do slope times the X data, the femur length, plus the intercept. Okay, before I apply, I know that the slope and the intercept are fixed, so I'm going to put dollar signs around them so that they don't change. Now apply, apply. So that gives me all of the y hat values. Those are the red points that I showed you on the picture in the slides before. Those are the model predictions at the input x values. Okay, so now we have a model prediction, model prediction and actual input y value, and now I can compute my residual error, and that's going to be simply y minus y hat. Apply it to everything, and it computes your residuals. Okay, so this is the residual at the first point, residual second point, third point, and so on and so forth. So that would be the difference between the red line and the blue points, okay, at each one of those blue points. Okay. Now, for interval calculations, I'm going to do interval quantities, or just intervals, Q's, or interval. Okay. And actually, let me move it one more column. So for cleanliness, okay, I'm going to do interval. So these are the quantities that will help me for my interval calculations. My sum SSE, or sum of the square of the residuals, right? So that's my SSE. That's equal sum of the squares of the residuals. Now there's a formula, there's a function in Sheets, we used it in the past, called sum squares. It takes a column, squares it, and sums it up. Okay, squares each value and then sums it up. And that's going to be sum square. Okay. And I'm going to choose this one, D. Okay? So that's the sum of the squares. So if I go back to what I'm trying to do here is first compute my standard error, which is square root of sum of the squares over n minus 2. Okay, so what I just computed is SSE, sum of the square of the errors. And next, I'm going to compute my SE, or my standard error. Then SE is equal to square root of sum of the square of the errors over the degrees of freedom, DOF. Okay? That gives me 6.08. Okay? Very good. Let's go back now to the slides. Now, these formulas, okay, so I have T alpha over 2, I have SE, I have N. X0 is the value where you're trying to make a prediction, okay? So that's your, what's a person's height at a femur length of 45 centimeters, okay? Or what's the precipitation at 84 degrees? That's your X0. That's the point of interest you're to make a prediction on. X bar is the mean of the data, so we need X bar. So X bar is the average of the data. X bar, this is going to be equal to average of your X data. So that's going to be your column A. Okay, and that is 46.308. Okay. Next, I need summation of X. Okay, so let's do that. So let's do sum X, summation of X, and that's going to be equal to sum of all the A values. Correct? Summation of all the X values. Now, in and of themselves, summation of X is meaningless. Right? Just look, what are you summing up all the femur length? But in the statistical sense, it's going to contribute to the answer, right? Okay, summation of X. And then the other one is going to be summation of squares of x, okay? This one, summation of the squares of x. Summation of squares of x, and that's equal to some squares as well of a. Okay? 286,775, whatever that is. Okay. That's really good. Right? Now, I can finally compute my error margin for the confidence interval and the error margins for the prediction interval. So CI error, so that's the error for your confidence interval, okay? And that's equal to T alpha over 2 times SE, et cetera, et cetera. So this is my critical T value times SE times square root of, I'm going to open parentheses. Let's see what we got here. 1 over n. So it's going to be 1 over n, this value over here, plus this one, n times x0 minus x bar squared. Okay, so that's going to be n times, again, open parentheses, x0, that's my x0, okay, minus x bar, that guy, and, okay, so I'm going to come here, squared, right? So that's going, I captured 1 over n, and this guy I need to put a, so this needs to be a fraction here. So, oh, here there's a plus sign, right? There's a plus sign. And then we're going to divide this by, I'm going to open parentheses in the new denominator, and I have n times summation of the squares of x minus summation of x squared. Okay, so that's going to be n times summation of the squares of x minus summation of x all squared. And it gives me an error. Okay, over n times L6 minus L5 squared, error unknown. Oh yeah, I cannot put n. I'm still used to Python. All right, so it gives me 11.52. That's too big. I think I made a mistake. So T alpha times SE times 1 over n. Hold on, I think there's a typo here. F4. Oh, hold on. I think I made a mistake here. It's F8, the critical T, F8 times L3 times square root of, okay, square root times F4. I think I have a mistake here because this is too large, I think, over F4. The I2? No, it's oh, the I2 is too large. Yeah. Okay, yeah, that's fine. Okay, so let's do 50 or something. Okay, yep. No, it's correct. Now, PI error, so that's confidence interval error. We do the PI error, and then we can find the bounds. So PI error for a prediction interval, you just copy and paste this nasty formula. Copy and paste it here. But all you have to do is add 1 under the square root over here. So 1 plus. Okay, so if I zoom in a little bit. If you remember, the PI interval had, in the margin of error, there was 1 plus all of this. Okay, now we're done. So for a, then you can do a CI lower and CI upper. And simply you say, okay, my CI lower is my model prediction minus my CI error, and my CI upper is equal to my model prediction plus my confidence interval error, and my PI lower is going to be equal to model prediction minus PI error, and my PI upper is going to be equal to my model prediction plus my PI error. So what this means, at 50 centimeters, for all people who have a femur length that is 50 centimeters, their average height is going to be between CI lower and CR upper at 95% confidence. It's going to be between 179.8 centimeters and 182.8. The average of that population of 50 centimeter femur carriers, okay? For the prediction interval, if I were to randomly pick a person from this class whose femur, and it turns out their femur length is 50 centimeters, then their height is going to be between PI lower and PI upper with 95% confidence. See the difference? So next time when you hear about a statistic that, oh, 5% of people are going to get cholesterol and whatever, or like, think, is this an average? Is this a confidence interval? Are they giving you a confidence interval or a prediction interval? Because the prediction interval, then you can say, okay, then what is my likelihood of getting that cholesterol or whatnot? But if they're giving you a mean value, then you're, on average, then you don't know. To make a prediction about yourself or if an individual, you need the prediction interval, okay, with a regression analysis. Okay? Pretty more powerful than what we did in numerical methods, right? Just giving you now confidence and other things, other information. Okay? So I will ask you about this in the exam. I will ask you about prediction, give you a person, like a population, pick a person. Okay, what should we use? Confidence or prediction interval? Or given a confidence interval of this and that, what does that mean? You need to be able to articulate that, or just choose the right answer that on average, if the population of, paints that are cured at 50 degrees temperature, then their hardness is going to be that much, okay? On average, versus the prediction interval. Okay. There's two more topics which I think might be worth covering. So one more thing you can do here is we can actually also do confidence intervals on the slope and the intercept. Okay, so we did the regression line. We did a hypothesis test on the correlation coefficient, whether the population is linear or not. There's a linear relation. But we can also, so once we build the regression line, we can also build the confidence interval on the slope and the intercept. Okay, we can build the confidence interval on the slope and the intercept. And the way we do this is not by hand, it's just we do it by using the XL minor. Okay, so for the XL minor, you can also do linear regression. It's a little bit more, got a lot of questions on it, but if you follow these steps, I'm going to give it the Y data here, input Y range, and then I'm going to go here and choose the input X range. This is the input X range, and actually I might have to just select the specific values. So I think for XL minor, you have to select the specific values. So A1 to A134, actually that's going to be the input X range, and the input Y range is going to be from B1 to B134. Okay, and just add labels. Confidence level 95%, so that gives me a significance level of 5%. And my output range, let's put our output over here, my output range. If you click OK, it's going to do a lot of things for you, okay? So that's the cherry on the top of the cream of the icing on the cake. So it does compute the R value for you. It does compute R squared. Okay, it does compute your standard error, it does do an ANOVA analysis. We're not going to worry about that here. What we're concerned with here gives you the intercept and the slope. So intercept, and this should be slope over here. It gives you the slope. Okay, so intercept and slope. Now, what's interesting over here, it also gives you a confidence level, a confidence interval on your intercept and your slope. So if the true population is truly linear, and we can represent it with a regression model, this would be the confidence interval on the slope, on the intercept and the slope. Okay? Now, those don't directly translate on confidence intervals for individual values. It just tells you that your true regression line for the population is going to vary between these two slopes and intercepts. Okay? Your true mean regression line for the population. Okay? There's multilinear regression. I think I'm just going to stop here, not overwhelm me with more column. Yes, yes. So actually, I am going to copy it into the one that I already, like this whole thing. Yeah. So I'm going to copy it into the other one, which I already shared with you. Okay, height and femur, this one. Okay? Does this make sense? Yep. So you should take next any data. So duplicate the sheet, plug in any data. It's going to give you the information that you need. Okay, just put in the data. So make sure you make this sheet sacred, like duplicate it 7,000 times. You know, use like a distributed storage system. So I don't back up my files. I just distribute them among friends, and they are my backup storage. So, so you know, distribute it and make sure you have a copy of it. Okay? And the slides are up there. I still have a few more minutes. Let me just make sure I covered everything on the slides, please. Okay, so there was one question that we did not answer on the previous thing here. When they asked this question, I want to answer this question. For each additional degree that the temperature rises, what is the increase in the level of precipitation? Okay, so that ties back to your slope. Okay, so that was the problem of precipitation versus temperature. Or for each centimeter that the femur length increases, how many centimeters does the height increase? Right, so you have the slope. You can calculate that value from the slope. Okay, and I have the answer for this one here. Okay, the slope of the regression line indicates the amount of increase of the y variable for each increase in unit in the x variable. So for the problem of precipitation and temperature, it was 0.225 inches of precipitation for each degree increase in temperature. For the femur data, the slope was, what was the slope? The slope was 2.83, okay, 2.83. So in other words, for every centimeter increase in your femur length, there is an expected increase of 2.83 centimeters in height. Okay, that's the other thing you have to consider. Okay, just the slope, rise over run.